So far, we've learned quite a bit about how the spinal cord generates motor action all by itself. Where does the brain figure into this picture? Let's look at the brainstem and the cerebral cortex, where the highest level of motor input to muscle cells resides. This high motor input connects to the final common pathway of muscle cells in your peripheral body through the descending input from the cortical and brainstem motor areas, which pass into the spinal cord to synapse on and modify the outputs of the very spinal cord circuitry we've been studying throughout this lesson. These inputs come down from areas high above the spinal cord, and they're capable of significantly altering spinal cord activity. A number of different nuclei in the brainstem and primary motor cortex provide the input to the spinal cord circuitry. Anatomically, these nuclei can be broadly defined into two parallel systems, which involve nerve projections through different areas of the spinal cord and target different musculatures. These two systems are the dorsolateral pathway, which runs through the dorsal or upper and lateral outermost part of the spinal cord and controls voluntary movement of the distal muscles, and the ventromedial pathway, which runs through the ventral or lower and medial innermost part of the spinal cord, controlling the proximal and midline muscles, which are essential for generating autonomic functions of maintaining posture and generating locomotion. Interestingly, these two pathways not only run through different paths and target different muscle groups, they're also controlled by different higher brain areas. While the dorsolateral pathway is under the direct control of the cerebral cortex and the midbrain, the ventromedial pathway is directly controlled by various nuclei in the brainstem. Inputs from the cortex are only secondary additions. As you'll see in the next lesson, this division is in line with the broader roles of cortex, which controls mainly voluntary behavior, and the brainstem, which is responsible for crucial autonomic and maintenance functions. You now know broadly what these two pathways do, but how do they function? Specifically, how does a command from high up in cerebral cortex or brainstem reach lower motor neurons with their cell bodies deep in the spinal cord? And how does this input affect the significant amount of independent processing we already know to be occurring in those neurons? As mentioned, the dorsolateral pathway controls our distal muscles, specifically those muscles involved in steering our extremities and engaging with the environment. Axons of this pathway end on two specific groups of lower motor neurons in the spinal cord. These neurons lie in the dorsolateral part of the spinal cord's ventral horn and are located in two specific rostrocaudal segments of the spinal cord. If you think back to the original segmental map of the motor neurons we discussed, which segments do you think these are? Well, we know that the distal muscles are those in the extremities, your lower arms and legs, hands and feet. So it makes the most sense for those dorsolateral axons to terminate in segments at the level of the arms and legs. And this is exactly what we observe in the spinal cord. In fact, there are so many axons terminating in these segments, due to the many motor units within the distal muscles, that the spinal cord's gray matter is slightly wider at these points. Note the cervical enlargement and the sacral enlargement at the levels of the arms and legs, respectively, in the spinal cord. This precise targeting allows the dorsolateral pathway to precisely control the distal muscles, even as the proximal muscles are held steady. Motor units activated by the dorsolateral path range in size and can involve quite a small group of muscle fibers. Thus, the dorsolateral path facilitates fine motor control through activation of small, specific groups of muscles in the extremities, allowing, for example, the movement of individual fingers. It's thus not surprising that lesions to the dorsolateral pathway can have a dramatic effect on our fine motor control. In the mildest cases of dorsolateral lesion, voluntary movements just become slower and less accurate. But more often, an individual loses the ability to make fine, independent movements entirely and is unable to, for instance, specifically move the fingers or wrist. This is due to the loss of modulatory control by activation of small, precisely arranged motor units, which is the specialty of the dorsolateral pathway. While fine motor activity is considerably impaired by dorsolateral lesions, posture, as seen in the ability to sit or stand upright, is completely spared. This latter point should not come as a surprise, since you know that the posture is controlled by the ventromedial pathway. This pathway innervates axial or midline lower motor neurons and interneurons, which in turn synapse onto midline muscles. These muscles keep our heads balanced on our shoulders as we navigate through space and turn our heads towards various sensory stimuli. The ventromedial pathway neurons also project collaterally to many segments along the spinal cord. These projections control groups of muscles along the body axis that are involved in posture and general balance, keeping the body stable and centered above the ground. As a result, lesions to the ventromedial pathways often result in difficulty maintaining a sitting or standing position and can render the body axis and proximal muscles immobile. However, such lesions leave the hands and distal extremities unaffected, since the dorsolateral pathway is still intact. One important point to remember is that these are simplified descriptions of the descending motor pathways. There's quite a bit of redundancy built into the motor system, and there's often more than one way for information to travel from the brain to the spinal cord. So damage to one pathway can often be compensated by a surviving path. However, even compensatory circuitry generally remains true to the dorsolateral versus ventromedial divide.